Okay, so welcome to lecture 3. What we are going to do now is we're going to move into something I sort of alluded to in lecture 2. At the end, I said something a little crazy. Organic chemistry is all acid-base chemistry. And I'm going to try to prove that, at least try to convince you of it. So before we launch into that, now that you're at lecture 3, before you continue, you really need to ask yourself that you have understood these concepts. And you should also be hitting your book to make sure that you get it, okay? So I would not proceed with this lecture until you have convinced yourself that you at least get these points. What is an atom? We talked about the nucleus, atomic structure, electrons. What are electrons? Those are sort of a pretty big deal when it comes to organic chemistry, right? And how those electrons combine to make bonds. Bonds are the fundamental component of a molecule. They hold the atoms together. And we discussed two different kinds of bonds, the sigma bonds, or that low energy bonds, and then pi bonds, higher energy bonds that exist in what we'll call pi clouds, right? And how electronegativity makes those bonds unequal, and we discussed that in the context of resonance. Okay, so these topics should give you you should have an idea of these topics. Okay, and now we're going to move on to acid-base chemistry. Now, acid-base chemistry, probably remember, very basic definition is you have one of these mineral acids like hydrochloric acid. It's got an H and it's got a Cl. And the chloride is a negative charge and the hydrogen or proton is a positive charge. And these have some sort of equilibrium. And in water, that equilibrium very strongly prefers to go toward a dissociation where the H plus is more associated with the water. So if we say this is water, right, the oxygen of that water will happily take that proton, and then you'll end up with something like that. And then we'll also have the chloride, and that's a Cl minus on that. That still stabilizes this overall structure here, this what you'd call a hydronium structure. So this is your classic Arrhenius definition of an acid base, right? So your classic Arrhenius definition is dissociates in water to give hydronium. All right, and the hydronium that is that fella right there. Bases likewise dissociate to give the hydroxide. So instead of sodium hydroxide, you would have used, instead of hydrogen chloride or hydrochloric acid, you'd have used sodium hydroxide. And you just, instead the OH would go deprotonate water, and, that would just flop around. You'd have sodium as a they dissociate, and they strongly do so. In water, these things don't like to be dissociated. And in water, we have a pretty convenient way of representing the extent of this dissociation, you'll remember, and that is this equilibrium right here. Okay, so we have this sort of equilibrium. And equilibrium, you'll remember, has some associated constant. That's a big K, right? And the big K in water dissociation is going between protonated and deprotonated, right? So if you just take water, water can become, so you've got water, all right, H2O, And you can imagine that just becoming, you can have two hydrogen, two H2Os, and those can disproportionate, right? Those can become an H3O plus and an HO minus. Okay, with some level of equilibrium between these two. All right, two H2Os can dissociate there. That equilibrium is probably pretty unfavorable, right? So if we were to call, what is the KW of the dissociation, right? Products of reactants, H3O plus HO minus, we'll draw that out there. That equilibrium is 1 times 10 to the minus 14. So water is going to probably, pure water is going to be somewhere, in the middle. So a neutral solution, right, is going to be right, times 10 to the 7. So that would be a neutral solution, which allows us to be pretty convenient. We'll call a solution acidic when this species dominates, when hydronium dominates, and we'll call it basic when this species, hydroxide, dominates, right? So in an acidic solution, you have a concentration of H3O plus, that is going to be larger than 1 times 10 to the minus 7. Okay, which means the acidic solution will have an HO concentration that is going to be less than, 1 times 10 to the minus 7. Okay. And yeah, well, those are really big numbers. That makes it somewhat inconvenient to write. So very clever people said, I'm not going to write all that scientific notation. I'm just going to declare a brand new, very specific for water pH scale, and that pH scale is going to be equal to the minus log. So that way we can get rid of this times 10 to the nonsense of whatever species. If we want to call it the hydronium ion, that we're going to call the hydronium ion, then we're going to call that the pH, or the acid, or pK, and that's going to be much more convenient. That way we can say neutral solutions, they have a pH equal to 7, and then acidic solutions, they have a pH less than 7, right? Basic solutions have a pH above 7. Now, you'll notice all these things, nary a single carbon associated with it. Arrhenius actually is not incredibly helpful with organic chemistry. The problem being that organic molecules, and we'll discuss this in a bit, very, very few of them, they exist. Actual carbon, hydrogen, oxygen species, but very few of them dissociate like HCl. HCl goes into water, boom, it's dissociated. That makes this really easy. That makes this chemistry, this math, quite easy. Organic molecules, take acetic acid, vinegar. That's an organic acid, and we'll talk about it in a minute. You put that into water. Acetic acid doesn't turn water into like super flesh-eating acid, right? Acetic acid, that just makes vinegar. Certainly concentrated acetic acid is probably not good for the skin, but acetic acid somehow is weaker, and so these simple definitions are a little bit harder to come up with in water, where they just don't fully dissociate. So we use something that in my opinion, is still not perfect, but it's a great secondary definition where we call it the Bronsted Lowry acid base. Now, the Arrhenius acid base and the Bronsted Lowry acid base are very, very similar. Basically, Bronsted acids are acids that can give a proton, right? Right, so that's our very definition of a Bronsted acid. Bronsted acid donates protons. All right, that's great. That is almost indistinguishable, though, from the Arrhenius acid. But where the big difference comes in is in the bases, right? So a Bronsted base accepts protons. Now that's a change, because the Arrhenius base has a base that goes in and dissolves. But you don't need to dissolve, right? If we remember back to the last lecture, a base is something that can just take a proton and maybe even take on its positive charge. So we can still have this HCl, classic Bronsted, classic Arrhenius. But we're going to stop with the Arrhenius. We're just going to stick with Bronsted. Classic Bronsted acid. It's got a proton, willing to party. Now, the base, it just needs to be able to accept it. And from our last one, we said a lone pair of a nitrogen would do just fine, right? So we'll say, ammonia. Ammonia, it makes meth, but it also burns your face if you screw it up. It giveth and it taketh. And ammonia is super good at takething protons, right? Just like we said before. It doesn't dissociate in water. You throw it in water, it just pulls the protons off of the water. So it's not the old-timey Arrhenius definition. It's the new-timey Bronsted definition, where this bad boy, those protons, they come and take that, all right? And then that then gives you a new species, a new protonated species, NH3, but it's got now a proton, and it's taken the positive charge. The positive charge, remember, goes on the nitrogen, because the nitrogen is the thing that's the electron deficient, because the nitrogen's electrons went to the protons to make it happy, so the nitrogen took the positive charge. And, written out, so that's all kind of written sort of, so it makes sense, right? But written out, NH4Cl, this is a compound called ammonium chloride. Okay, you can buy that in a bottle. And so this is a bit easier to use, right? Because now you can use lone pairs, you can use all sorts, you can even use pi bonds, because pi bonds are electrons, right? They can even be bases. They can take a proton, the electrons will go and grab a proton, and you will end up with basically the conjugate base, all right? So as a review, what's the conjugate base? All right. So in this particular example, you have your acid. I'm going to erase this little line. I'm going to write it. You got your acid, and you got your base. What do they make? Well, your acid makes a conjugate base. So the acid goes and makes the conjugate base. All right? It's a conjugate base. It's got a negative charge here, right? So that's electrons. In theory, I guess, those electrons can go and deprotonate something. They won't. It's a terrible base. That chloride is super happy being negatively charged, but it's gone from, as you'll recall, a super strong acid to a super weak conjugate base. Very, very typical, all right? That also means that if you started over here as a base, you ended up with the conjugate acid. So this is your conjugate acid. This is your conjugate base. Okay, so this ammonium chloride, it is an acid. Not a terribly good acid, but it is an acid, right? That proton can come back off. It's way more reversible than throwing HCl into water, actually. So I can even extend this equilibrium arrow. So there's a bit more of an equilibrium of them shifting back and forth in this process. Okay? Now, this is still somewhat limiting, right? The Bronsted-Lowry definition still really seems to depend upon a proton, but there's actually no real reason why you even have to have a proton. I mean, if you think about it, an acid could just be anything that'll take electrons, right? Because a proton will take electrons. That's what it's doing. The H plus is taking the protons of this right here. It's taking those protons. So the most recent and contemporary definition of an acid base was proposed by G. and Lewis. And that's what we tend to stick with. And we'll shuttle back and forth Bronsted acid and Lewis acid. But the Lewis acid base that is, I think, a little bit better for organic chemistry, right? Is that you don't need the transfer of a proton. You can call something a Lewis acid if it just accepts a lone pair of electrons, okay? And as a consequence, forming a new bond. All right, and then a Lewis base, that then essentially is almost the same as a Bronsted base. It just donates a pair of electrons. With the proviso that it form a new bond. Okay, so it's a far more general definition, all right? And the prototypical Lewis acid is going to be in small molecule sense. You'll remember we talked about boron, right? Little boron had an empty pi orbital, or had an empty p orbital here, nothing in it, was happy that way, but it will take a lone pair, right? And if you show it nitrogen, these lone pair will go into that empty orbital. So boron is perfectly capable of accepting the lone pair of nitrogen, creating this charge-separated boron species, where the nitrogen, where the boron now takes the negative charges and the nitrogen now takes the positive charges. And in the context of what we're going to talk about, Lewis bases don't necessarily even have to be boron. Lewis base can very easily be a metal. It could be, say, let's say it's iron. Let's say we go with iron, right? Iron. Right? Iron is a couple of oxidation species, and iron usually has a couple positive charges here. We'll say that's iron 3. And iron 3, that can, the lone pairs of, say, water, they just love iron 3. Well, they'll go over here and they'll form coordination complexes with iron. And in this way, iron is acting as a Lewis acid, pulling in the Lewis basic sites of the water, okay? And so this also is much more helpful as a definition in the context of organic chemistry, because as I said before, you can have carbon atoms, right? So carbon, we got your sigma bond. We always said that. We said that that's really not going to participate with, and we got our pi bond right here, right? And you've got these things, right? This pi bond actually is even capable of forming some complexes with, and we'll get to this, like palladium metals and stuff like that. So this Lewis acid base, that comes in handy right there. Okay? So that is sort of the fundamental of how acidity and basicity works. This sort of a refresher for you. Now, the difference between acidity, there's the relative magnitude of how strong an acid or base is. That is expressed as something called as a Ka. So if we wanted to talk about acid strength, we'd have to talk about it quantitatively, okay? So if we have an acid, and we're going to go back to like a Bronsted acid, HA. So that HA is going to co-dissociate. It's going to go dissociate presumably in water, and that water is going to form hydronium and the anion is going to go someplace else. So it's going to form two different complexes. And there's going to be some equilibrium associated with it, and that equilibrium is the equilibrium of acid, or the Ka. And so the Ka of a compound, the more it favors the formation of products, because remember, equilibrium is product over reactants. Right? The more it moves this way, the more it prefers becoming hydronium, the stronger the acid is, right? So let me just let me just move this a little bit up because it's, here we go. The stronger the acid becomes, right? Because you see, so the stronger the acid becomes as the equilibrium favors dissociation into hydronium. And remember, in water, hydronium really is sort of the acid you have to be worried about. So any acid is going to react with water. They just sort of have to react with water when you get in water, because water is simultaneously an acid and a base. It may be worth reviewing a bit of Gen Chem just to catch yourself back up on that. But the strength of an acid is based on this pKa. So it's a big K, and that's going to be equal to the negative log of Ka. Very analogous to pH, but I want to emphasize this. pKa does not equal pH, okay? The pH of a solution is how much free hydronium ions you have, how many free protons you have. The pKa, the pH of a solution has nothing to do with the acid you add. You can add any acid you want and you can get a pH out of it. The pKa really kind of tells you, like if you want a pH of 1, all right, and you're throwing in something that has a pKa, a max pKa of 3, good luck to you. You're going to really have to drive that home. But the pKa is a constant for a given acid, referring to the pH where half of the acid is ionized. And the pH refers to the concentration of hydronium ions in a solution, right? So how do you generally predict the relative strengths of an acid? And generally, an acid is really strong when the anion is super, super happy being an anion. So the strength of an acid is going to be it's dependent on a couple of things, right? Sometimes it's dependent upon the electronegativity of something. So if you have a couple things that are, you can imagine, all right, carbon with some protons, nitrogen with some protons, oxygen with some protons, fluoride with some protons. say, which one of these are going to be the most acidic? And you can already probably assume that it's this HF down here, because the HF is a known mineral acid, and that forms fluoride and a proton pretty easily. And you can probably guess that water, you kind of already know, that's got a pretty solid equilibrium as it splits into hydroxide and a proton. Now, ammonia gas, that's not going to really split too much into a proton. It's not going to become a proton anytime soon. And of course, methane, that's just ridiculous. I mean, that's not going to ever dissociate in any appreciable amount. But the cool thing is, we can actually quantify it now with pKa. So a pKa will give us our relative acid strengths. Well, you say the pKa down here is 3.2. We can even give this a title. pKa is 3.2, which is, that's pretty acidic. Water has a pKa of 15.7, or controversially 14. You'll find sources of both. It's the craziest thing in chemistry that we can't really seem to agree on what the pKa of water is. But for this discussion here, it doesn't much make a difference. The pKa is somewhere intermediate. And it also represents, remember, these are logarithmic. So pKa jump here is like 12 units, right? So that's 12, that's like 12 orders of magnitude, right? So an increase of 3 to 4 units, a pKa of 3 to 4, that's a jump times 10. pKa from 3, 4 to 5, so difference between 3 to 5, that's times 100. So the acidity difference of 12 orders of magnitude is enormous. And then going to this, it's like 36. So that's even enormouser. And then you get up to here and the pKa is like 50. It's almost impossible to calculate. So that's like the enormousest pKa you can imagine. Essentially, there's no dissociation from the carbon of a stable molecule, which is good. You don't really want the carbons in your body dissociating into free protons anyway. Otherwise, you turn into like a soup or something. Now, bigger atoms seem to sort of contradict this electronegativity. And so things like HF, that's a tiny little atom, fluorine, HCl, HBr, HI. Okay, so odd enough, you can do the same sort of thing. There's an equilibrium associated with all of these. And HF, as it turns out, associates in the F minus and an H plus, and it's got a pKa of 3.2, like we already said. HCl is way stronger. It's like -7. Okay, so that dissociation is super, super good. HBr, -9, HI, -10, which is interesting because this probably contradicts what you think of HF as being some sort of crazy killer acid. Even though it's weaker. Well, that's a funny thing about acids, right? So HF is in fact comparative to the other mineral acids fairly weak. But the fluoride ion that it produces when it dissociates, that'll go off and form basically an irreversible bond to calcium, creating calcium fluoride. And that's like crazy. It'll go and it'll pull that right out of your bones. And HF has this awful propensity to get into your skin. It just like goes in through your skin. So HF actually does a terrific job of dissolving your bones. And in principle, in theory, it could even do that while you're still alive, right? Because HF's not going to really burn your skin, but it'll go in and it'll eat your bones. And that is like a rumor, because HF, the calcium in your blood, the fluoride will pull the calcium out of your blood and give you a heart attack way before it dissolves all your bones. So you'll be dead while it dissolves your bones. So working with HF is actually fairly dangerous, and you have to have a good gel of calcium gluconate. So if you were to spill some fluoride HF onto your skin, you have to rub yourself down with this calcium-rich gel. in order for the fluorides to go attack the gel instead of your bones and your blood. So, yeah, pKa is in everything when it comes to being dangerous. But as you can see, it's not. This danger doesn't come from the fact that it is a strongly dissociative, and there's actually a reason, and we'll get to it in a bit and later on in this course. And it actually has something to do with the fact that hydrogen and fluoride actually kind of like each other quite a bit because they're both like really small. The electrons are really close to the nucleus in both cases. They are quite a bit alike in that regard, and so they don't really want to break up. Hydrogen and iodide really can't be more different. Iodine is an enormous atom, and its electrons are just like going everywhere. They're sloshing about, and that sloshing creates something called polarizability. Hydrogen is like the super hard ion. It really doesn't want to be around something so free-spirited. So as you get to these bigger atoms, they tend to fall apart. All right. Now, what about organic molecules? Because this is organic chemistry, and this all should, in principle, be reviewed from Gen Chem. Organic molecules, of course, tend to be a bit different, right? You can have, let's just do some acetic acid, all right? Acetic acid. O and then H, okay? That's acetic acid, and the pKa of acetic acid is 4.7. So acetic acid's weaker than the weakest mineral acid. So, acetic acid's vinegar. And acetic acid, you'll remember, has a proton here and here and here, right? So that's a carbon, and at the end of a carbon, that's CH3. Now, what if we make it variable at this point? We just say, obviously there's going to be a proton. We're going to call that R, and we're gonna vary that. And so it's a 4.7 when R is equal to a proton. That's just acetic acid. But what happens when we start adding, say, we make it an iodine, or we make it, just increase the electronegativity to bromide, to chloride, to fluoride, right? What happens as we increase the electronegativity? Well, you can imagine as we increase the electronegativity, the want for electrons to go this way increases. And so as that want for electrons pulls this way, this oxygen's interest in holding on to this positive charge goes down, right? As you're sucking electron density out of it, the proton becomes more free to leave. And so all the way down here with your most electronegative fluoride, you get 2.59, okay? And chloride, 2.86, then 2.9, and then even iodine is at 3.18. So the electronegativity starts to, you can see, really play. And this effect, where like somehow like the electronegativity is just being pulled through these, crap, I didn't want to erase that one, through these single bonds, or these carbon-carbon bonds, that's what's called an inductive effect. Okay? Inductively pulling the electrons through the carbon-carbon bonds, through this carbon-carbon framework. And the inductive effect, it's really dependent upon how far away this R group is. This R group's actually, only got 1, 2 carbons between them. But you keep adding carbons, this inductive effect goes away. Now, there's another effect that's associated, not with like the electronegativity of an atom, but the resonance structures of an atom can actually just make pKa's and the acids and bases really non-intuitive. And so you've really got to think about the resonance effect. And we touched on the resonance effect a little bit in a former lecture. So resonance can lower electron density too. And we're going to right quick, just to have a quick recap of what is resonance. And so resonance always involves like these double bonds. You already got to look at double bonds. You see a double bond, you think, all right, that is a structure of convenience. All right, this is one way to draw a nitro group. It turns out that's fine. You draw that, every chemist on the planet will know you're drawing a nitro group. It does not accurately predict that this oxygen is going to be negatively charged all the time, and this nitrogen is going to have, well, the nitrogen was always going to be positively charged, but it doesn't predict that, like, this oxygen right here is not going to always be statically uncharged, right? Because these electrons, that can go back onto the nitrogen, and that can go back up on the oxygen to give you a different structure, right? So you can have a structure where you've got an R group where this oxygen is down here, and I'm going to draw a resonance arrow. And I've drawn this, right? So I've drawn it so where that goes up here and that goes up there. And now I've drawn in principle two different structures, right? But have I drawn two different structures, right? I've drawn a very special arrow here, by the way, called a resonance arrow. It's not the equilibrium arrow. It's not one of these, right? That's a different kind of arrow. A resonance arrow means these are two of the same structure. These are identical structures, all right? These are compromise in saying, I cannot really get away with drawing something that looks like this. Much to my chagrin, I can't really draw something like this. I mean, I guess I could, where I've got like the electrons sort of smeared around here, and that's a plus, and then there's like a minus on the inside. In fact, this is probably the best way to draw it, but it's a bit cumbersome, and it really, the resonance structures become very cumbersome if you want to try to show a distribution like that, especially when one of the atoms is more electronegative than the other. So in principle, neither of these structures are actually correct. I guess this is probably the most correct, but we just kind of got to live within our ability to depict stuff. And this weird distribution of electrons here, resonance. Okay, that's called resonance, all right? Now, in organic chemistry, I sort of already gave it away. The double bonds are involved in resonance, and so we do have to have some rules, right? So in resonance, only, let's call these resonance rules, only pi bonds, okay, resonate. Sigma bonds are just too low energy. They're not going to really, I mean, the electrons in a sigma bond are being shuffled around. They are forming different sort of things. They're moving around. But it's really the pi bonds and sort of their weaker interaction between the two atoms that allow them to sort of slosh around very, very liberally. Okay. Now there are these rules. Only pi bonds can resonate, and they must have valid Lewis structures. Your resonance structure cannot somehow magically make 5 bonds to carbon, right? You cannot start off and have a carbon that starts off with 4 bonds and then add a negative charge. No, that's 2, 4, 6, 8, 10 electrons. Bad. You cannot do that. That makes your organic chemistry professor sad, okay? So, and as we always emphasize, you can only move the electrons. All right, don't try to move the nucleus. They're too big for you to lift. All right, so leave the nuclei alone. The nuclei are fixed. That's why we just use a letter, so that you don't try to push around the letters. Only the electrons move, okay? And the number of unpaired electrons should be constant, right? So if you start off with 2 unpaired electrons, you end up with 2 unpaired electrons. All right, so keep unpaired electrons constant. Oh, run out of space. Let's move this over just a skosh. Okay, now question is how does resonance influence acidity, right? So let's consider pKa of some organic molecules, all right? We're going to go back to our friend acetic acid. That's got a proton. And it's got an equilibrium associated with it. And that equilibrium basically says, we already said, that the dissociation tends to prefer actually forming an anion and freeing up that proton to go participate with something else. All right, and it has a pKa, as we've already said, of about 4.8. Let's consider another molecule, CH3CH2OH. All right, ethanol. Ethanol also has an equilibrium associated with it. It's got a free proton. And it's got CH3CH2O. Let's be consistent with our colors here. O minus H plus. All right, now these are dissociated. It got a pKa of about 16. That's pretty big difference, right? That's about 5, that's 11 orders of magnitude. And in both cases, the negative charge is on an oxygen, right? So what's the difference here? Now, remember that a key to acidity is all about taking those electrons and just making them happy. If something really, that oxygen really doesn't mind holding on to the electrons in that bond, it's going to be more acidic. Just like if we go back and remember, methane isn't acidic at all because carbon absolutely does not want those electrons. It's not electronegative. It doesn't want those electrons. HF is acidic because F wants those electrons. Perfectly happy to take the electrons off the fluoride, off that FH bond. So the H drifts away. So there must be something in here that's entertaining the electrons a little bit better in the acetic acid case than in the alcohol case. And it turns out that is resonance. So we can redraw this molecule. That's a resonance structure where we have, just like in the nitro group, we can draw O minus, and we can draw a resonance arrow, and we can draw an O minus up here and the O down here because these are two resonance contributors. And in my estimation, how I would draw this is basically like this. This is an easy way to draw it, so I'm going to make it this drawing. These electrons, these pi electrons, are shuttling around here, right? So I think this is more of your fair representation of what your resonance structure looks like. That means that if you consider alcohol, ethanol over here, right? We draw in our typical chemistry nomenclature. Carbon, oxygen, right? These electrons are stuck on your oxygen. There's nothing over here. These are just hydrogens, all right? These are just CH3s. They don't want those electrons. There's nothing pulling those electrons back. Those electrons are stuck on that oxygen, and oxygen, having no place to dump them, is not super keen on letting go of that hydrogen, that proton. It kind of wants to hold on to it, whereas over here in the acetic acid side, all right, that proton, these electrons are now like distributed over 3 atoms. Like you've taken the electron density and you've really smeared it out. Okay, it's like a delicious New York bagel. It's like all over the place. Suddenly, because you could distribute electrons over 3 atoms instead of just like confining it to 1, this resonance has really stabilized that anion. And so you end up with a resonance stabilized compound. And as a consequence, because you can smear electrons over multiple atoms, that means that you can stabilize. That makes it more acidic. So the better you have the ability of taking those electrons and distracting them with like an inductive effect, like an electron withdrawing group, or a resonance, or a pair of shiny car keys you can dangle in front of them, anything to distract the electrons and pull them away and smear them over, that's going to decrease your pKa of your structure. Now, I already alluded to this. We're still looking at a resonance structure where you've got two of the same sort of same atom. So that resonance structure is shared fairly equally. And so you don't have to have that sort of equivalent sharing, right? So that's something to keep in mind. That was covered in a previous lecture, so I'm not going to necessarily cover it again, but you also want to keep in mind in a resonance structure, what I've done here is I moved pairs of electrons. I didn't move individual electrons, okay? So I'm going to give you a brief example of something you ought not do, right? So I didn't take this. Okay, so that's good form. That's good resonance. You can't break the bond and put the electrons wherever you want. So truly, acetone in this particular case, it does indeed have a resonance structure where you can take two electrons and just like clobber it up there, right? And you can end up with something that looks like this. And this is something we discussed in a previous lecture. So no real reason to necessarily go into this. Now that I drew this as purposefully because oxygen, being the more electronegative form, will take those electrons. You can draw this. I mean, the electrons could go, I guess, the other way. Let's make this purple to show that this is a different resonance form. You can do that and form this. That is a valid resonance argument, but it's utterly inconsequential. This is just not going to contribute anything. Like the idea of the negative charge going on the carbon and a positive charge going on the oxygen is not right, because oxygen, that loves electrons. Carbon's more or less indifferent to it. But it's still a valid resonance form. What's not a valid resonance form is if you were to take one electron from the pi bond and like stick it there, and one electron from the pi bond and stick it there, and create like some funky diradical like this, where you have a one electron there, and like there's a radical electron here. That's not a real resonance form. You have to move pairs of electrons simultaneously, right? And so really, when you talk about a resonance form like this, I sort of like to imagine, acetone having this structure, and then sort of like painting the electron density so that you know that the electron density sort of prefers like this. So if you imagine an electron density, it's more like this, where the electrons are going to hang out way more often over here around this oxygen than they are here. And so that's sort of your painting, right? Because it's hard to draw this little squiggle thing, right? Because that's not truly accurate. So this is probably better than my effort that I would say to draw this, but like, how do you draw the little dotty thing? Like the dots mostly align up here. The electron density prefers here. And that's a long-winded way of saying none of these are good pictures. None of these are good. This is probably the best. This is nonsensical. And this is what we're going to draw because it's convenient, okay? But by no means does that mean that's necessarily right, okay? So that is the lecture for this particular thing, for this particular section. What you hopefully took from this is you got a refresher on pKa and pH. And you know, they're not the same. And you hopefully took away that resonance affects pKa, okay? And how that resonance affects pKa through charge distribution, okay? And we will move on to how we'll do a little bit more resonance pushing and dipoles in the next lecture.